So with larger degree polynomial functions, sometimes it's a little bit intense. So like on this one, I would have to find 4 answers, and I'm not even given a starting point. So we can use what's called the rational zeros theorem to narrow down our options. So first of all, recognize that we're using rational numbers. So numbers that can be written as the ratio of 2 integers. So these are all fractions. These will not include imaginary numbers. Let me write that down. What is not included in this theorem? Imaginary solutions, which we can also call complex, and then any irrational solutions, like the square root of 2 or the square root of 3 or e or pi or anything like that. Okay, none of those will be included in this theorem. So basically what we're saying is I need a starting point. Where does this thing cross the x-axis? I know I'm looking for 4 different places, or 4 the same places. I don't know. Okay, what are we going to do to narrow down our options? Should I try 33? Does 33 work? I don't know. Rational zeros theorem is going to narrow those options down for us. So I've got my last digit is 3, and my lead coefficient is 1. So what I'm going to do is put the last number, which is 3, over the first number, which is 1. And this is slightly misleading. This is not your answer, okay? What I'm going to do is find the factors that will multiply to this top number. So what can I multiply together to get 3? I can multiply 1 times 3. Okay? Do the same thing for the bottom. What can I multiply together to get 1? Well, that's pretty much 1. From here, I'm going to take every factor in the numerator and put it over the denominator. So in this case, it's literally going to be 1 over 1, which is 1, and 3 over 1, which is 3. So notice that I'm going to put a little plus minus here. That plus minus means that these rational solutions can be positive or negative. So 1 over 1 gives me a 1. 3 over 1 gives me a 3. And now for your sanity, I'm going to write this out. So this can either be positive 1, positive 3, negative 1, negative 3. So I'm going to put 1, negative 1, 3, and negative 3. So here's what we just learned. If this polynomial, when I graph it, is going to cross at a pretty place on the coordinate plane, meaning not complex and not irrational, it's going to be in this pile. So would it cross at 5? No. 5 is a pretty possibility. It's not in my pile. Would it cross at negative 2? No. Negative 2 is a pretty place on the coordinate plane, and negative 2 is not in my pile. So this is a good starting point to find our potential solutions. This doesn't guarantee that these are the solutions. It just says pull from this pile when you're trying to find it. So let's try it again. We now have g of x equals negative 6x to the third minus 5x squared minus 2x plus 2. So I'm going to use rational zeros theorem, which you're going to see me abbreviate it like this, rational zeros theorem. So I'm going to use the rational zeros theorem to narrow down my possibilities. So I'm just not grabbing stuff blindly. Okay, so what did I do up here? I need the last number, which is a 2, and I'm going to put it over the first number, which is a negative 6. You're going to see I don't care that it's negative, because I'm going to handle the positives and negatives when I get to this step. So what do I have? The top number is a 2. The bottom number is a 6 that I don't care is negative. So I need to find out all the numbers that I can multiply together to get a 2. So that's going to be 1 and 2. And what are my numbers to get multiply together to get 6? Well, I can do 1 and 6 and 2 and 3. So those are my possibilities to multiply together to get a 6. So in order to be strategic, I'm going to be very methodical so I don't miss anything. So I'm going to take the first one over everything on the bottom. Then the second one over everything on the bottom. Then the third one, if there was one, over everything on the bottom. So 1 over 1 is 1. 1 over 2 is 1/2. 1 over 3 is 1/3. 1 over 6 is 1/6. So now I'm done with him. So now take 2 over everything in there. So 2 over 1 is 2. 2 over 2 is 1. He's already there. He's in my pile. So I don't need it. 2 over 3 is 2/3. 2 over 6 is 1/3. He's already in my pile. Don't repeat it. So if this polynomial is going to cross in a pretty place on the coordinate plane, not imaginary solutions and not irrational solutions, it's going to come from this pile. So I don't need to try 5. 5 isn't in this pile. I don't need to try 3. 3 is not in the pile. So how do I list this thing out? And just to be methodical, I'm going to put it in somewhat of an order. I'm going to do the whole numbers first, and then I'm going to do the fractions. So I've got positive 1, negative 1. I got positive 2, negative 2. I got positive 1/2, negative 1/2. Positive 1/3, negative 1/3. Positive 1/6, negative 1/6. And that's it. Okay? So of all the places that this polynomial could cross my x-axis at a pretty spot, it's going to come from this pile. So if it's not in this pile, don't try it. So now let's actually put this to work and see what we've got. Oh no, it's folded. Okay, so I've got find the zeros of f of x equals x to the 4th plus 9x to the 3rd plus 18x squared minus 30x minus 100. And I'm supposed to find where this thing hits the x-axis. So I'm going to find 4 answers. I'm going to find 4 answers. I'm not given a starting point. So I'm kind of flying blind right now. So I'm going to say, let's use the rational zeros theorem so I don't waste my time. So what is the last number? The last number is 100. I don't care that it's negative. Over the first number, which is 1. So I really only need to find the factors of 100, because anything over 1 is just itself. So what can I multiply together to get 100? I can do 1 and 100. Okay, I can do 2 and 50. So I'm making a list. I'm just going through and increasing these. So does 3 go into 100? No. Does 4 go into 100? Yes, it does, 25 times. Does 5 go into 100? Yes, it does, 20 times. Okay, does 6 go into 100? No. 7? No. 8? No. 9? No. 10. So that is my complete list. Okay, and theoretically, I would put all of these over 1. So my list for rational zeros theorem is kind of long. But it's positive 1, negative 1, positive 2, negative 2, positive 4, negative 4, positive 5, negative 5, positive and negative, positive and negative, positive and negative. So if it's in this pile, it's worth trying. 3 is not in this pile. I'm not going to try it. It's going to waste my time. Negative 7 is not in this pile. I'm not going to try it. It's going to waste my time. And now we're just going to dive in and find our solutions. So this is where it gets a little bit tedious. I always start with 1, just out of a habit. So I'm going to start with 1, okay? And then I am going to use synthetic division to see if it spits out a 0 at the end. If it doesn't spit out a 0, that means it didn't work. If it does spit out a 0, that means I have a solution, okay? So 1, 9, 18, negative 30, and negative 100. I had to pause. 4, 3, 2, 1, 0. All right. So I'm looking for zeros at the end, and I have not cheated. I have not used my graphing calculator, so I don't know what the solution is. So I'm doing how you would do it. I am just setting it up and seeing if I can find an answer. So 1 times 1 is 1. That gives me a 10. 1 times 10 is 10. That gives me a 28. 1 times 28 is 28. That gives me a negative 2. 1 times negative 2 is negative 2. That gives me a negative 102. That's not a 0. That's not a solution. Okay, so I'm just going to keep going till I find 1. So now I'm going to try 2. 1 did not work. Let's move on to 2. So here's a 1. 2 times 1 is 2. That gives me 11. 2 times 11 is 22. That gives me 40. That gives me 40. I know how to add. All right, so I'm sorry. 2 times 40 is 80. 80 minus 30 is 50. Oh my goodness. 2 times 50 is 100. That gives me a 0. So out of the 4 that I'm looking for, I just found one of them. There's 3 more out there. So I'm going to put a little pile up here. Zeros. So I'm going to go over and try negatives at this point. So I got an answer of 2, and I'm going to shut my study door because I'm a stupid dog. Clam! Hush! She's always quiet till I start recording. All right, so I found 1, I found 2, so now I'm going to go over and just try some negatives, okay? So let's try negative 1. Negative 1 is in my pile. Let's try it. Now here's the cool part. I found a 0, which means I can now drop this down and I can use this row. Okay, so go back to our example of 24 over 6. Does 24 over 6 reduce? Yes, it does. It reduces to 4. Okay, can I break down 4? Yes, I can. So that's what I just did. I just took something big and I found out something that worked. So something big, I found something that worked. And now I'm going to break down what's left. Now I'm going to break down what's left. So I'm going to start with this row now. And that's going to kind of sort of help me along just to knock this thing out. So I've got a 1. Negative 1 times 1 is negative 1. That gives me 10. Negative 1 times 10 is negative 10. That gives me 30. Negative 1 times 30 gives me negative 30, which gives me 20. That just wasted my time. Irritation. So let's try negative 2. So I'm still going to use this row. So negative 2. Now hang on a second, because go back to a few seconds ago or a few minutes ago. And what I did before was I factored what was left. Okay, this does not factor down. Where am I at? This does not factor down. This is an x to the third plus 11x squared plus 40x's plus 50. That doesn't factor. If it did, I would factor and be done. But it does not factor. So that's why I'm keeping trying. As soon as I find one more answer, I'll drop this down to an x squared, and then I can manhandle what's left. So I have a 1, an 11, a 40, and a 50. So negative 2 times 1 is negative 2. That gives me 9. Negative 2 times 9 is negative 18. That gives me 28. Negative 2 times 28 is negative 56. That gives me negative 6. Didn't work. So I'm still going to find something else. So let's try. I'm not going to try negative 3. It's not in my pile. So let's try negative 4. 1, 11, 40, 50. So I have 1, 11, 40, and 50. And I'm trying negative 4 at this point because negative 3 is not in my pile, so it wouldn't work anyway. Negative 4 times 1 is negative 4. That gives me 7. Negative 4 times 7 is negative 28. That gives me 12. Okay, negative 4 times 12 is negative 48. That gives me a negative 2. Still didn't get my 0. Okay, so negative 5 is in my pile. Let's try negative 5. 1, 11, 40, and 50. So here's a 1. Negative 5 times 1 is negative 5. That gives me 6. Negative 5 times 6 is negative 30. That gives me 10. Holy cow. Negative 5 times 10 is negative 50. That gives me my 0. So where are we at? I just found out that 2 worked. Now I figured out that negative 5 works. Okay. And now where am I at? When I found this answer, this was an x to the 4th. That dropped me to an x to the 3rd. So I've been working with an x to the third the whole time since that point. Now I'm working with an x squared. So I'm going to fill this in. That gives me a 1x squared plus a 6x plus 10, and I need that to be 0. So my first question, is this factorable? Do I know two numbers that multiply to 10 that add up to 6? Well, my options are 1 and 10. That's not it. And 2 and 5. That's not it. So I need to do one of two things. Either use quadratic formula or complete the square. This is set up for completing the square. And I like completing the square if I can. It just makes it a little bit cleaner. Okay, so how do you can do quadratic formula at this point. I'm not going to. I'm going to choose to complete the square. If you do quadratic formula, you'll get the exact same answer I do. So to complete the square, I'm going to get all of my variable terms on one side and all of my constants on the other. And then how do I complete the square? I take half of what was my middle term. So half of 6 is 3, and square it. Okay, so half of 6 and square it. That gives me 9. I just created a 9. But why did I create it? Make sure you create it on both sides. Because now this factors down to x plus 3 times x plus 3. So this, in algebra world, is a perfect square trinomial. So that gives me x plus 3 squared. Negative 10 plus 9 is negative 1. Okay, how do I do this? This is now square root method. I just completed the square. Now I'm in square root method. So let's take the square root of both sides. Don't forget your plus minus. On the left, your x plus 3 pops out. On the right, I have positive or negative. What is the square root of negative 1? It is I. And I'm almost done. I need to solve for x, so I'm going to subtract 3. Subtract 3. So I have x equals a negative 3 plus or minus I, which means there's my two other solutions. Negative 3 plus I, negative 3 minus I. So let's come back over here. Negative 3 plus I, negative 3 minus I. So I'm looking for 4 solutions. 1, 2, 3, 4. I found all 4 solutions. So let's come back here just to do a quick refresh on complex numbers. Negative 3 plus I, negative 3 minus I. I is imaginary. Negative 3 is real. So I have a real plus or minus and imaginary, and that makes for a very complex situation. So this is a complex number because I'm adding and subtracting reals and imaginaries together. This is a complex number. I'm adding and subtracting reals together. So even if I just had something like new problem, if I had negative 7i, that is still a complex number because I could say 0 minus 7i. So real plus or minus imaginary. So anytime you're dealing with imaginary solutions, you're dealing with complex numbers. And that is it for Module 7.